All right, so welcome to the first practice session. Today it's Numpy. So Numpy is kind of like the foundation of all matrix related stuff that will come after. So scikit-learn and PyTorch is all built upon Numpy. So you can think of them as a MATLAB for Python. So I'm pretty sure at least like most of you have used MATLAB during your undergrad. So it's very similar. The syntax is very similar, and it's a Python library that lets you easily manipulate n-dimensional arrays. So n-dimensional arrays meaning, vectors can be one-dimensional array, matrices are two-dimensional arrays, and then like there's three-dimensional, four-dimensional arrays as well. And it can contain integers, floats, bools, so you can manipulate them easily. And as I said, it's the foundation of modern deep learning. So neural networks are just a bunch of matrix multiplications, as you see here. So you just constantly linearly transform them and then, push them, put them through nonlinear activation functions. Then again, you just multiply them, dot product them, and then comes the output. And it integrates well into these applications. You can see that SciPy and scikit-learn, TensorFlow, PyTorch. So we will learn scikit-learn next week, and then from the third week, we will learn PyTorch. So, yeah, tensors. So tensors meaning n-dimensional arrays. So n-dimensional arrays in TensorFlow, PyTorch are very similar to NumPy n-dimensional array. So they have their own ways of, so NumPy arrays are the ones that run on CPU and the memory. And PyTorch and TensorFlow, they have their own, data structure, the matrix-like or n-dimensional array data structure that runs on GPU and VRAM. And they are both quite interchangeable, and their syntaxes are pretty similar. There are certain differences, but they're pretty much similar. And if you have any question, always refer to this API document. So you can click them and then see it for yourself. And yeah, so as I said in the intro class, all practice sessions, including all projects, 3 projects, will be done on Google Colab. So there's no way I can provide over 300 GPUs for every individual in this class. So thankfully, Google is providing this something called Colaboratory, which is an online Jupyter notebook where you can freely use their GPU or TPU, actually, GPU or TPU for 12 hours. So it's a session-based. So if you close your tab, as you see here, if you close your tab, you lose your data. But then there's a way to save your data to Google Drive. So on Google Colab, you can connect to your Google Drive and then load or save your files, your progress to Google Drive. And then, after 12 hours, you can save it to your Google Drive and then open a new session, load that saved file from your Google Drive, and then run again. So you can actually keep going and going. But none of the projects or none of the class material will require you to run things more than actually like several minutes. So don't worry about that. So you can click this link and then the Colab website will open for you. So if you don't like the session-based stuff, then you can, as I said in the first class, you can install local Anaconda. And if you have your own GPU, or actually you can train on your CPU as well. So you can train it locally, train your models locally. Right, so let's move right on to Colab. Right here. So I've uploaded the IPython notebook file for today's practice session on Classroom. So hopefully everybody downloaded it. So you can upload that on Colab and then open it. So then you will see this screen here. So I'm hoping everybody's on the same page as I am. 다 이거 열으셨나요? 지금 이 화면 다 보고 계신 거죠, 지금? Right. Okay, cool. All right, so we'll wait maybe 20-30 seconds for anyone who is actually downloading the notebook from Classroom right as of now, and then we'll begin the practice session. Okay, so I think we can begin. So before you actually do anything on Colab, you have to have your own runtime kernel. So if you well today we don't need GPU, but if you click this runtime and then you can change runtime type. Here this is where you can select whether you want to use CPU or GPU or TPU for that matter. But I don't think we're going to ever use TPU in this practice session because TPU has a little bit more constraints on what kind of things you can do and what kind of things you can't do. So GPU is a little bit more flexible. And oh, you can see that they actually okay, so they do have options for selecting A100 and V100, but well, it's grayed out, so I'm not sure why they're here. What types of GPUs are available in Colab? Oh, okay, I see. So yeah, actually you can have a paid subscription for Colab. So it's very, very cheap. It's like a couple dollars a month, I think. So I guess when you have a paid subscription, then that's when you can use A100 and V100. But here we're actually all just we're using the free service. So T4, which is a little bit like a kind of a weak, like low tier GPU, it's enough to do everything for this class. So you can click this. But for today is Python 3 and CPU. You don't need GPU for today's class. So save and then click connect. Here, you can click connect here. Then you're actually asking for a session, asking for like a virtual CPU and a virtual RAM and a virtual hard drive. All right, so we're connected, and then import NumPy. And here are some functions that I've defined for the practice purposes. I don't think we're ever going to use check these, but we're going to use print object function very often. So click this. So, all right. So, well, before anyone, like before we move on, if there's someone who has never used Python notebook before, I said that Colab is an online Python notebook. So if you downloaded Anaconda and then ran Jupyter notebook, then you must be very familiar with what I'm doing. But if you haven't, then Python notebook is an online. Well, it's not an online. It's like it's a very user-friendly, interactive Python interpreter. So if you run Python interpreter in a terminal, it'll look like this. Give me just a second. All right. So if you run Python terminal, if you run Python interpreter on terminal, then you actually just Python, and then you have to do everything here. You have to define your function, define print object, something, and then return 1, then call print object 5. Well, it'll return 1. So yeah, everything needs to be done here. So if you like when you run code, or actually when you're writing code, you have to be very careful not to make any mistakes while you're doing anything in the terminal version of Python interpreter, which is very inefficient, and it's not very friendly for developing stuff. So and trying out different stuff in a very fast time. So you can use instead what people usually use is a Python a Jupyter notebook. So here you can write stuff and then so each cell is executable on the cell. So you execute it, and then when you execute that, this executed result will be stored in the memory. So you can reuse its output. Well, here we've imported the NumPy library. So all the cells afterwards know that NumPy was loaded, is imported. Somebody's asking me that the 클래스룸 공간이 개설되지 않아 교수님 있던 저기 뭐 그럴 리가 없는데 이미 클래스룸에 한 330명 계시는데 혹시 다른 그 뭐죠 링크를 클릭하신 게 아닌가요? So yeah, I'll continue. So as I said, all the following cells will remember the executed results in the previous cells. So that's what's good about Python notebook. So you execute this, and then you execute this, and then afterwards, all the cells afterwards, below, will know print object. So when you use print object in the following cells, it'll know it'll work. So that's what's really good about the Python notebook. I mean, Jupyter notebook. So we're going to start with scalars, vectors, and matrices. So I said that NumPy is very good at handling n-dimensional arrays. So there's 0-dimensional array, and then there's 1-dimensional array, and there are 2-dimensional arrays. So you can see the difference. This is a scalar value, this is a vector value, and this is what this is. So when you execute this, it works. And then when you print those three things, three things, then you can see that this is a scalar, this is a vector, and this is a matrix. So far so good. Like nothing's no, like, yeah. No biggies here. I think people are still talking about the class sum thing. Yeah, I think people are trying to use class sum on KLMS. I've created a separate KLMS. So you should read the notice in the KLMS. So there is a notice, 공지사항 있죠? 공지사항을 읽어보시는 게 좋을 것 같습니다. Right, we're moving on. So yeah, and there are a couple of property functions that you can use, such as ndim. Ndim is the number of dimensions. So scalar has no dimension, vector has 1 dimension, and a matrix has 2 dimensions. So when you print this, then you can see like A is ndim. So A is this one, A is this. A's ndim is 0, B1, C2, obviously. So no, like very straightforward, right? And shape is something that we'll use very often. So shape is the dimensionality, the number of dimensions per axis of your n-dimensional array. So as I said, scalar is a 0-dimensional array, so there is no shape at all. This is just empty tuple. And B is a vector, so it should have 1-dimensional tuple to represent the shape, so which is 3 dimensions. So you can see it's a three-dimensional vector, right? And then there's C shape, which is 2 by 3. So you can see it's a 2 by 3 matrix. There are 2 rows and 3 columns, right? So it's 2 by 3. So ndim and shape, please keep that in mind. And then we're going to move on to higher dimensional arrays. So scalar, vector, matrices, we've dealt with them very, very often. We are very familiar with that, but we're going to go higher than that. So you can see D and E are here. D and E are here. Oh, actually, I should open. Oh, sorry about that. Actually, I should have opened this year's. It's the same thing. Don't worry about it. It's the same thing. Okay, no wonder there was all the outputs from each cell. All right, so moving on. We've looked at until shape, and now we're moving on to n-dimensional array. So D and E. So please execute it yourself. See what D and E looks like. So if you click this, then you'll see D is more than a matrix. It's a 3D matrix. It's a tensor, so it's a 3D matrix. So there is 2 matrix 2. There are 2 by, so there you can see that there's 1 2 by 3 matrix. Then there's another 2 by 3 matrix, right? So there are 2 2 by 2 matrices. Can you repeat about the shape? So C looks like this. C is a 2 by 3 matrix. That is why the shape is 2, 3. All right. So we're moving on to higher dimensional arrays. So D is a 3-dimensional matrix. So its dimensional, its ndim is 3. The shape is 2, 2, 3. As I said, it has 2 2 by 3 matrices. 그러니까 2 by 3 매트릭스가 2개 있으니까 2 by 3 매트릭스가 2개 있으니까 2, 2, 3, 2, 2, 3가 되겠죠, 쉐입이. And then E is 1-dimensional higher. So you can see E is like there's 2x3 matrix here, another one here. So that's already two 2x3 matrices. But then that is again repeated one more time. So there's two of 2x3 matrices. So that is why it's 2, 2, 2, 3. Okay, so it has a nested structure. So innermost is actually innermost is just scalar, but then it is expanded to a vector, then expanded to a matrix, expanded to a 3D array, and then expanded to 4D array, 4-dimensional array. So easy, right? Right. So quiz. So I mean, yeah, this is don't like this is not anything anything all the quiz that I've shown here has nothing to do with bonus points that I talked about in the intro class. But if you're interested, you can volunteer to answer the question anyway, just for fun. So please define this in your terminal. Yeah, 2x3 1. Yeah, 2, 3, 1. Oh, okay, good. So all the quiz today, actually, you can just write it here. So A equals NP array, copy here, and then print. Oh, you can just actually print a shape. Yeah, so easy, right? So we're going to move on. 2x3 by 1. And before that, this is kind of a waste of dimensionality because the innermost is 1, which is equivalent to just having no dimension at all, no structure at all. Because I've actually gone a little bit overboard and put the square brackets here for each element in this inner vector, right? Or should I call it inner? Yeah, it's like this right here, inner vector. So this has 3 elements inside, but each element it's on its own a single dimensional object. So we could have easily write it down like this, right? And then it would still be okay. Like there's no syntax error, and it would have a compact 2x3 dimensional shape of the object shape. But I've actually gone overboard and put like square brackets for all individual matrices just to make my point. So it was 2x3 by 1. All right. So defining NumPy arrays. So far we've actually manually defined the NumPy arrays, but that is actually very, very inefficient. You don't want to write manually. If you want to create like a large zero matrix, you don't want to do that. So there are certain convenience functions such as ones. So it gives you an NP array filled with ones. So here it's just 10-dimensional array. I'm sorry, 1-dimensional array of 10 elements, which is just 10D vector actually. So this is a 10D vector. And if you write it like this instead, this is 10, but now it's 2x5, right? So you can imagine what's going to happen here. It's going to give you a 2x5 matrix filled with zeros. Okay. Then next one, NP full, it's same. It's going to give you a 2x5 matrix, but it's going to be filled with 5s because you've defined it 5 here. And the random is random. So if you go to the API doc here, so documentation, API reference, you can, right. Okay, here we go. You can search for whatever you want. So and numpy.random.random. This is the function that I just used right now. So what is this function about? This is a function that gives you any random value in a half open interval, 0.0 to 1.0 exclusive, 0 inclusive, 1 exclusive. So it's I guess it's a uniform random number generator. Right. So random, and then 2x3 by 4 obviously is going to give you back a 2x3 by 4 n-dimensional array, 3-dimensional array. And you can see all the numbers here are between the 0 and 1. And if you want to use if you want to sample from normal distribution rather than a uniform distribution, then there is also some other function called random and numpy random normal. Oops, normal. So numpy random normal, if you use this instead, then you can set its mu and sigma. So location is the mean and scale is the standard deviation. So you can use this function instead if you want to sample from a normal distribution. Good. Next one we're going to use is very, very, very often. NP range is starting from 0 up to this number. Well, actually, 1 minus this number. You can see that it leads up to 9. So 10-dimensional vector starting from 0 to 9. And then this one is actually giving you a different type. So this was an integer. If you use NP a range, then it is going to give you an integer filled object. So if you want to convert that to a float type, then you put as type float with a dot operator here, Then it will give you a float version. And this one, obviously, is going to give you 0, 1, 2, 3, 4, 5, all the way to 9, but in a shape that looks like this. So this is a reshape function. Well, actually, I think we're going to have a bunch of reshape examples in the following cells down below. So this much is the same as this much, right? So it's going to give you a vector of 0 to 9, and then you're simply reshaping that to a 5x2 matrix form. 5x2 matrix form. Right. So quiz. So you can go ahead and try to create this by yourself. 4x3x2 tensor field matrix. Yep. Very good. Very easy. Actually, I'm assuming that like at least 80%, 90% of people today already know what NumPy is. Hopefully, I'm helping someone. Like, I'm not wasting my time here. Cool. Nice. All right, so we're going to, oh, well, actually, I can just try to copy one answer. Yep, as you can see, 0 to 23. Well, actually, the spec was 23.1. Sorry, 0.0 and 23.0. So it should have actually been a float type like this. So if you just end at reshape, then it means that you haven't actually carefully read the spec, which is bad practice. When you do a coding interview in future IT companies for job interviews, then you should always check the spec. If you just read whatever the coding interviewer tells you and then just start writing code, you're going to have a bad time. All right, moving on. So never forget this one, S type. Moving on to indexing and slicing. So there's a bunch of stuff here, but this is all just different examples of, accessing an element in your object or accessing a subset of element in your object. So we can start from, well, we should actually comment out. Bunch of stuff here. Right. And then run it. So you can see obviously what's happening here. So this is accessing each one element at a time. So A0 is 0, A1 is 1. So this is A, right? This is a 10-dimensional vector. First element 0, second element 1. This is all the same. And you can see that this is following the syntax of C or Java, right? Well, because it's the element of a vector starts at the index 0, not index at 1. So is 0 is the first element, 1 is the second element, and -1, -1, is the last element. So this is where things get interesting. So you can access the last element without actually having to memorize the number of the size of the vector. traditionally, how you would access number 9 here, the last element, is that you need to memorize this is a 10-dimensional array. So you put 9 here. But instead of that, you can just simply put -1 and then write directly access to the last element without actually having to memorize how large the vector is. Is A10 equal 10? I don't think so. You can try it out. A10 should probably give you a syntax error because this is a 10-dimensional array and you're asking for 11th element. So you can try that. And so negative is not, it just doesn't end with the last element. -3 is the third element from the back. So it's -1, -2, and -3. So it should be 7. So you should be familiar with this. We're going to use this negative very, very often. Right, so moving on to the next set of elements, next set of examples. So you can see what's happening here. There's a new thing. There's a new operator, which is the colon. And so A is this, and A 0 colon 10 is against the same thing. A 0 colon is the same thing. Colon 0 is the same thing. Colon is the same thing. So it's all the same thing. So you can see that they're interchangeable. So what colon it does is it's a range, right? So what you're doing here is you're asking for the elements between, starting with 0. So this is inclusive. So first index, first element, 0th, the 0 is the first element, right? So the first element all the way to the last element, because this is 10-dimensional array. So the last element should be written with 9, but this is exclusive. So this is inclusive, this is exclusive. So you're asking for the entire element by calling this A colon 10. So that is why you're getting this. And you can actually omit 10 here, which is like 1 after the last. So this is actually the 11th element, as I said. So if you omit this, if you omit the 10 here and write it like this, then automatically Numpy will understand that you want the last one. So it will actually give you the same thing. If you omit the first one, it'll also understand. Numpy will understand that you want to start from the first. So that is why it gives you this. If you omit both sides of the column, so there should be 0, there should be 10 here, but you've omitted both. But Numpy still understands that you want to start from the top, start from the first, and go until the last. So that would be this. But then why would you do this? You can just call A. If you're going to do this, then there's basically no difference than calling A. So you can play around. You can actually type A colon 5 and see what happens. Oops. What am I doing wrong here? A colon 5. There's I've written 0 somewhere. Oh, okay, here. Okay. So if you call A, null or blank colon 5, then obviously you're going to go up to the 5th element, right? And you can start from the 5th element, actually. You can start like this. Then it'll give you 5, 6, 7, 8, 9, the remaining 5. You're starting from here. So you're starting from the 5th element. So that would be the 6th. Sorry. So this would be actually, you're starting from the 6th element because the index starts from 0, right? So this is the 6th element. So 1, 2, 3, 4, 5, and then 6th element. Right. Okay, moving on. Oh, yeah, here are some practices. I'm just going to show you and then we're going to move on. So starting from the 7th element, getting the remaining 5, and starting from the 3rd element, and then going up to 5th element. So 2, 3, 4, right? Moving on. So you can execute them and see what happens. What would be -4 colon? -4 colon. Right, 6, 7, 8, 9. Yeah, because you are starting from the 4th element from the back all the way till the end. So that would be 6, 7, 8, 9. And the next one, A colon -5, -8 would be. -8 would be. I think some people, Yeah. Right, it should be 0, 1 because you're starting from the first. You're starting from the first because there's an omission. There's an omission here. So you're starting from the first and then you're going up to the 8th from the back element, which would be 2. So yeah, 0, 1. 0, 1. Right. Moving on to the next set of so this is a little bit interesting. You can see that, so A is this, and then when you write 0, 10, 2, you're only getting the even numbered positions. 0, 2, 4, 6, 8. So that is because you've written down 2 here. So you're skipping every other element. So this is increasing your index jumping by like 2. So this is 0, 2, 4, 4, 6, 8. If you write a 3, then obviously you're going to get 0, 3, 6, 9. Right? If you write 4, you're going to get 0, 4, 8. If you write 5, you're going to get 0, 5, and that's it. So that's basically skipping. And if you write 2, 6, 3, then you would obviously get 2, 5, 2, 6, 3. So how do you interpret the 2, 6, 3 is you want the element from the the third position, which is this, and then you want to go up to the 6th element, which is 1, 2, 3, 4, 5, 6, the 5th element, right? And then you want to skip by 2. So hitting every other third, right? So that's 2, skipping 2, and then third, so it's 2, 5, right? So that is what you get here, right? And then the last one is -1. So -1, -1, and so this is going backwards. So you're skipping there should be 0 and 10, but you've omitted, right? So it's going from the first to the last, and then there's a negative direction. So it's going backwards, actually. So you start from 9, and then you're going back to 0. So if you want to go back like this, 8, 7, 6, then you need to write 8, 5, -1, because you're going backwards. So 8, 5, -1 gives you 8, 7, 6. And if you just simply write 8, 5, it doesn't give you anything because this doesn't make sense because you're starting from the 8th element and then you're going to go up to the 5th element, which doesn't make sense. So it's going to give you an empty vector. So you need to write -1 if you want to go backwards. So that's how you get 876, right? So how would you create 963 then? 963. It's good that there are already different types of answers. So good, yeah, good. Good. Yeah, we can just try one of the answers. Yeah, there's no one right answer here. I'm going to take any random stuff and then print it out. Give you 963, but there are other ways to do this. So hopefully everybody's on the same page here. And then we're going to move on to indexing a matrix. So we've gone through like a lot of core details of indexing a vector. Indexing a matrix is just an expansion of indexing a vector. So please run this and then see for yourself. This is a 3x3 square matrix, and 0, 0 will give you the first element. 0, 0 will also give you the first element. So you can use whatever you want, but this is kind of like this syntax is more like the traditional classical programming language stuff, like C or Java, but you don't want to write that. This is way easier. 0, 0 is way more, like easier to type in. And then print object A11. So if this will give you what? This will give you the second row, second column, which is 4. So you get 4 here. And how to access the last row. So if you've closely followed how to access the last element in the vector, the previous cell, then you would know how to access the last element. Yeah, you can write A3, but that's not what I'm getting at. Yeah, A-1 would be the right answer. And how to access the second column. So this would be, how to access the second column. Yeah, it's A column 1. So A column 1 will give you print object A, colon 1 will give you, yeah, 0, 1, 2. I'm sorry. Oh, actually, no. So 0, 1, 2. Yeah, okay, so that was my mistake. So what this gives, so the accessing of the second column is actually this. So 147. We want second column 147. So yeah, I guess I've skipped the detail a little bit. So you can see that before the comma is the row, right? Here, this is the row, this is the column. So this is the first dimension, second dimension, and it's separated by column. And how you would access a certain column, that means that you need to go through all the rows. So you need to go row inclusive. So actually this would be 0, 3, 0 column 3, which means that you want all the rows and you want only the second column, right? So that's what this is about, 147. But as I said, you can omit the first and the last element between the column and get the same output, 147. Okay. Yeah. Hopefully this makes sense. So this means that before the colon, you're accessing the row. And by writing simply just the colon, you're accessing all rows. And after the colon, you're writing 1, which means that you only want the second column. So that's why you get 147. So quiz again, how would you make 8, 5 using A? So you need to like slice and dice A. So what you would do is you first need only the third column, and remember that the order of the elements are in reverse. Let's see if one of the answers is correct. Page 5, correct. Yeah, very good, very good. Again, there's no one right answer. There's multiple ways to create this. Let's see what happened here. So we're going backwards in the, so yeah, we're going backwards. So the row is going backwards, and then we're getting the last column. So I guess that's okay. So if you execute this only with this, then you would get reverse ordered rows. So yeah, reverse order rows. Oh, excluding the first one. Why would that be? Interesting. Oh, okay. So we should have started with -1. Okay, so sorry. Okay, so this one's exclusive. This column here is inclusive. This is the end. This is exclusive, and this is the skipping thing or negative thing, right? So we're actually excluding the first row when we're going backwards in row. So you get this, and then all you need to do afterwards is just access the third or the -1 column. Then you would get A5. All right. So moving on. So this was indexing and slicing and dicing matrix. So next one is obviously indexing and slicing 3D tensor. So you need to first define the 3D tensor like this, and then if you access the third row, second column, first, well, I guess there's no name for that. First element or whatever. So second row meaning, the third row meaning that there's 1, 2, 3, 4. So we want this one because it's the third element. Within this, we want the second element. So we want this, and then within this, we want the first element. So we want this. So, no, sorry, this. So that's why you get 14, right? So what would A0 be? A0 would be obviously this guy, right? So A0. Oops, okay. A0 would be, as I said, the first guy. And A0, 1 would be within this, we want the second row. So it will be 2, 3. It will be 2, 3. And how would you create this? Then 2, 4, 6, 8, 6, 8, 10 out of A. How would you create this? So 0, 2, 4, 6, 10, 6, 8, 10. So you need to carefully only select like the first two, and then only the first columns here, right? That's how you will get 0, 2, 4, 6, 8, 10. All right, moving on then. We've got a lot of things to cover, actually. So conditional indexing. So this is a bit of a trick sometimes that you would sometimes use when, accessing, like manipulating your matrices when you're handling your neural network model. So let's try this out. So A looks like that. A is a 2 by 3, 3 by 2 matrix, and your index is A. What do you call it? It's a mode, right? So as A mode as 2 equals 0, which means that you only want the even numbered positions, even numbered, including the zeros. So it's 0, 1, 2, 3, 4, 4, 5, right? It's 0, 1, 2, 3, 4, 5, and you're asking for only the even numbered positions. That is why you get this, right? So this is 0, 1, 2, 3. Sorry. So we're actually comparing this, whether each element of A is divisible by 2. Each element of A, meaning 0, 1, 2, 3, 4, 5. Each element of A, whether it's divisible by 2. And the answer is true, false, true, false, true, false. Okay. If it was 1 divisible by 3, then this would be 0, false, 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 true, false, false. Okay. All right. So once we have that, where we can use this is actually, I haven't write it down here yet. Print object A index A index, and see what happens. You only get 0, 2, 4 because you're only accessing by putting this object inside the index here, then you are saying that I only want the 0, 2, 4, these elements. So that's why you get this. Okay. So this is a conditional indexing. All right. You can actually play around with this. Like I want any element that is larger than 2. Okay, larger than 2. And you don't need this. Then what happens? Then anything larger than 2 is 3, 3, 4, 5, right? 3, 4, 5. So you would only get 3, 4, 5. Right? So this is conditional indexing. So sometimes you might need this when I don't use this very often. I mean, when I was writing codes and then, building models, it wasn't very often that I use this function, but sometimes it really comes in handy. So keep this in mind. And taking specific elements. So, actually, we've already done that. So, yeah, you can do this. Yeah, taking specific element. I'm not sure why I put it here. Just 0. Yeah, you can take any arbitrary number of elements from this. Well, oops. Yeah, like this. So you're arbitrarily taking like the first and the third and the fourth element, but this doesn't even have to be in order. You can go like 9th element, 6th element, and see what happens. Yeah. So 0, the first element, the 9th element, and then the 6th element. So when you're individually selecting the elements, it doesn't have to be in order. Right. So moving on to taking elements from tensor. All right. This is not a tensor. This is a matrix again, actually, but just for the sake of argument. So what would happen if you select elements like this, right? So there's a comma here. There's a comma here. So before the comma is the row, after the comma is the column. And what you're doing is you want to take all the rows, and you only want to take the first, the third, and the fourth column, right? So the first, the third, and the fourth column. So that's why you get this, right? In the next example, what you do is, so there's a comma here. So you're taking all columns. You're taking all columns, but you're only taking the first, the third, and the fourth rows. So that is why you take only first, the third, and the fourth rows, and all columns. So that is why you get this, right? So all very, 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 straightforward. And then there are a couple of more examples, like tuple indexing and the array indexing, which is a little bit more involved. So when you take the tuple indexing, this you can look at here. So this is it gives you like a couple. The first tuple is the row tuple. The second tuple is the column tuple. So you get first row, second column element, first row, third column element, second row, first column element, sixth row, and fourth column element. So that is why you get 4 elements here. That's how this works. That's how the tuple indexing works. And the array indexing works a little bit differently. So you get this instead, right? So you're getting what? You're getting first row, second row, sixth row here, and then again, second row, third row, first row, fourth row. Oh, I actually made it. Yeah, second row, third row, first row, fourth row here. You get this, and then you're nesting them. See how this index itself is already nested? It has 2 square brackets here. It's nested. And you're putting them inside this bracket here. So that is why you get a higher order tensor. You started with 2-dimensional array, but you've arrived at a 3rd-dimensional array because your n-dimensional, your ND array indexing started with a nested index, right? All right. And then there's one last trick that we can use pretty often, which is ellipses. So suppose that you have a very, very, well, I can't print. I didn't print that out. It has how many? 1, 2, 3, 4, 5, 6. It has 6 dimensions. So it's a 6-dimensional tensor or 6-dimensional array. And its shape is this. So it has 2 rows, 3 columns, and 2 elements. There's no name for it. It's like, yeah. So each element, each dimension has this number: 2, 3, 2, 2, 2, 2, 2, 4, 3. And if you want to access a certain element here, then, for example, you only want to choose the second row and the third last dimension. Let's call it third element. Yeah. So the second element in the first dimension and the third element in the last dimension, you want to choose that. And what you would do is you need to actually write as many columns as there are here, right? So you should write like column. So column. So you need 5 columns here. 1, 2, 3. Not columns. Commas. So 1, 2, 3, 4, 5 commas to show that you are going to take all the elements between these 2 first and last dimension. So instead of doing that, you can just write ... instead. So that would be way easier for you too. It's just time saver, right? So it's the end result is the same thing. So whether you write it like this or whether you write it like this, the result will be exactly the same. So if you have like a bunch of, repetition, then you can use these ... ellipses anytime you want. Right, moving on to the math operations then. So this was just slicing and dicing and indexing and taking subsets. So we're going to go to math operations. So first we start with the summation, addition, subtraction, and multiplication and division. So we have two objects, A and B. A is this, or A range from 0 to 5, 3 by 2 matrix. B is filled with ones, so it's ones like this. And then when you add them, when you subtract one from the other, when you multiply them together, when you divide one by the other, it gives you this. Right. And note that when you write ones, it gives you a float value. When you write a range, it gives you integer value, interestingly. But when you add them, subtract them, divide them, multiply them, it gives you automatically, the output is automatically a float value. So it's actually that this A matrix is internally converted to a float value. When one value is one object is integer and one object is float value, and you try to mix them together by doing some math operations like division or multiplication or summation or subtraction, internally this guy will be converted to a float type value and then move forward. So that's why you get all these float type outputs. Right. And then there are some unary operations such as like sum, and there are some interesting tricks that you can use here. So this is A, and when you call sum function, it'll add everything up without, regardless of the shape or anything, regardless of how, like whether it's a two-dimensional array, three-dimensional array, it doesn't matter. You just add them all up, and then you'll get a scalar value out of it. But when you have axis parameter defined, then it'll actually use that specific axis to add. So you can see when you set axis equals 0, it adds by the first like horizontally, like by the first dimension. So you add these three, you get 6. You add these three, you get 9. So when you want to add by column, like horizontally, then you want to use axis equal 1. Then you sum by this direction here, so you get 1. This direction you get 5. This direction you get 9. So 159. So please keep that in mind, and don't get confused between the axis notations like 0 and 1. Like when you want to add this way down, you need to use axis 0. When you want to add horizontally, you need to set axis equal 1. And the same goes with higher order tensors. So be very careful with the axis number. Same goes with taking the mean. So if you average them all out, then you get a scalar value of 2.5. So basically it's 15 divided by 6, right? 15 divided by 6 elements, you get 2.5. And A max is taking the maximum value, A min is taking the minimum value. And you can use the same principle here. Instead of doing mean, instead of doing this, you can set axis equals 0, and see what happens. Then you'll get average value across this vertical bar, which is 2, and an average value across this vertical bar, this second column, 135. So 135 is 9, summation is 9, divided by 3 is you get 3. Okay. So same goes with max and min. Any unary operation, you can always use this axis value and then take whatever value you want. All right. And then we go to the dot product. Questions. Just want to clarify. So when we are using the star and so multiplication, division, and the A and B are the matrix, they don't multiply the matrix, but multiplying by dividing each. Yes, exactly. It's an element-wise operation. When you want to do actual matrix multiplication, this is where we're going to talk about it. Matrix dot product and matrix multiplication. Good. Yeah. Good question. So this is a element-wise operation. Moving on to the vector dot product. So dot product, hopefully everybody knows what a dot product is. Same as for vectors, it's inner product, right? So you have one vector, you have another vector, and then the dot product is multiply this two, multiply this two, multiply this two, and then sum them all up. So it's 0, 1, 2. So sum them all up, you get 3, right? So very easy. So what you want to use is something called dot function. So this is also dot, but there's the dot function. So this function is what you want to use when you want to do a dot product between two vectors. When you move to the matrix multiplication, then you can use 2 different techniques to do it. So this is A, this is B. So 3 by 2, 2 by 3. So when you multiply them, when you do a matrix multiplication between the two, you will get a 3 by 3 matrix. So there's one way to do it is using dot. Another way of doing it is actually using the at operator. And both will give you the same output. So this is very clear. And Cecilia, I think this is what you were looking for. Yes. If you go to the higher dimensional tensor, though, things get a little bit weird. So this is A, and A's shape is what? A's shape is 4 by 3 by 2. And B's shape is 4 by 2 by 3. 4 by 2 by 3. So one matrix, or we're going to call it tensor. One tensor is 4 by 3 by 2. Another tensor is 4 by 2 by 3. And you want to do a matrix multiplication between them. And there are two ways to do about it. One is using dot. Another is doing at. And at is actually a little bit more intuitive. So what we usually want to do in machine learning is the first element is usually the batch dimension, because when we're doing a batch, like batch gradient descent or like mini batch gradient descent, you usually take the first element to be the batch dimension. So how you can interpret this is there are 4 3 by 2 matrices in your training sample, and there's another 4 2 by 3 matrices in your training sample, and you want to multiply them together, multiply the two together. So it could be like 3 by 2, like 3 pixel 2, like an image of 3 by 2 resolution, like 3 pixels width and 2 pixels horizontally. So you can see this as like 4 like very low resolution images, another 4 very low resolution images, and you want to multiply those two matrices together. Then how you would want is you want to take 3 by 2 and 2 by 3, multiply them, so you would get 3 by 3 matrix, and you want to repeat that 4 times because that's the batch dimension. So you want to get 4 by 3 by 3 output, and at operator is what gives you the 4 by 3 by 3. If you use the dot product, if you use a dot operator, then you would get something else. 4 3 4 3. So this is weird, right? You're multiplying 4 by 3 by 2 tensor and 4 by 2 by 3 tensor, and you're getting 4 3 4 3 out, which is one dimensional higher than the input, which is a little bit weird, unintuitive. So usually what you would want to use is this, A at B. And if you wonder why this dot operator gives you such a weird output like this, then you can refer to this numpy dot. So if you look at numpy dot, if n-dimensional array is like m-dimensional, if A is on like some higher dimensional array, and B is also higher dimensional array, where this is larger than 2, then you would get some product that is like this. So basically what's happening here is this is internally multiplying this guy with this guy, this guy with this guy. So those two are collapsed, and that's why you're getting 4 3 4 3. So I'm not sure when we are going to use this in any practice. It's mostly going to be this that we're going to use for multiplying higher order tensors. Right, moving on. So we're now moving on to shape manipulation. So we've already seen the reshape operator a couple times. So we're just going to see a couple of examples like that. So what's happening is you're starting with the A range. So you would get a single vector that starts with 0 all the way ending up to 23, but you're reshaping them to 3-dimensional tensor. So 2 by 3 by 4. So obviously, the multiplied value of these 2 times 3, which is 6, times 4, which is 24, should be exactly the same as this. If you mess that up like this, you're going to get a syntax error, right? Because shape this doesn't match with size 24. So you want to be careful. Actually, you can omit this and then write -1, and it'll actually take care of you, right? So you can always write -1 for that one dimension that you don't have to calculate by yourself. Like this is determined. Like if this is 2 and 3, this has to be a 4. So the NumPy library will take care of that for you. But just to make sure, you want to write it 4 like this. Oh, there's already an example here. Yeah, like 6 by 4, 6 by -1 is going to give you the same output, right? And what would this look like? You can try it for yourself. What would what would be the shape of this D object here? Because we're doing something weird. Like A is already 24, size 24, so 6 by 4 is already okay. But why are we adding one more -1 dimension here? Yep, exactly. It's going to give you 6 by 4 by 1. So we're actually creating a additional dimension, which is not really useful. Yep, 6 by 4, 6 by 4 by 1. Moving on. So adding an extra dimension is what we actually just did. We just added an extra dimension by reshaping like this, but there's easier way to do it actually. So you can call none here. So A is just a vector, but when you call a function like this, like there's a colon here and then you put none, when you put none, then it's going to give you a one extra dimension. So actually we should shape. Right. So 3 by 1. So we're just simply just adding one additional dimension that has no particular use for as of now. And then quiz. So how do we make NP1s 3 by 4? How do you make a 3 by 4 matrix into something that is higher order, a 4-dimensional tensor, 3 by 1 by 1 by 4, using reshaping and none? Right. Which would be easy, right? Yep, exactly. It's A none none. So A colon none none colon like that. Or I guess we could also use A colon -1 1 -1 -1 and colon, I guess. But it's the same thing. Cool. Yeah, very good. Moving on. So stack and concatenation, this you will use very, very often. Concatenation function, you'll use it very, very often. So let's run it and see what happens. So A is a 3 by 2 matrix filled with ones. B is a 3 by 2 matrix filled with zeros. And AB V stack. So V stack gives you a vertical stack. So A, so you can see AB, you're calling this V stack function, and then inside you have a list of matrices, and the order is A, comma B. So you put A first, and then you stack B below. So that is why you get V stack like this. H stack is horizontal stack. So you can see you can expect what to happen. It's basically this. So you have A and B here. Well, yeah. I mean, yeah, the highlight is wrong, but this is A and this is B. And if you can add as many elements in the V stack or H stack. ABA will give you A, B, and A. So this V stack and H stack is actually a little bit more intuitive when you use these functions with matrices. But when you use functions, when you want to concatenate like higher order tensors, like 3-dimensional, 4-dimensional tensors by a specific axis, then it's much better idea to use something called NP concatenate. I think in PyTorch is PyTorch concat, but in NP is concatenate. So what's happening here is that you call the concatenate function, put the list, and then you have to specify the axis. So you want to concatenate these two matrices, A and B, along the first axis or along the second axis, and see what happens. So when you're concatenating along the first axis, which is the row axis, then you get a V stack. When you want to concatenate along the second axis, which is the column axis, you get a H stack, right? And this would give you a pretty good idea. With concatenating two tensors, two three-dimensional arrays, whose shapes are 4 by 3 by 2 and 5 by 4 by 2 along axis 2, would it work? Type it in and then see what happens. Yes, the answer is no. It'll give you a syntax error. So because you're trying to concatenate along the last axis, if you want to do that, then at least the first preceding two axes should match between the two. Otherwise, they won't concatenate. Yeah, left dimension should match. Right. So yeah, you get an error. So yeah, that won't work. Yeah, so remember this function, concatenate function. So you should always be careful with which axis you want to concatenate the two or, any elements in with respect to, right? Right, moving on to the transpose is transpose, so there's nothing much to learn. When you want to transpose a tensor, though, it becomes a bit interesting. When you want to transpose a tensor, which is like at least like through 3 or 4 or 5-dimensional matrix, 5-dimensional array, see what happens. So this is your A, which has a shape of 4 by 3 by 2, and you want to transpose them, then you don't use this large T. You actually use a transpose function, NP transpose. NP transpose A, and then you have a list. So what does this list do? What does this list do? It actually, you write it down. You've written 0, 2, 1, which means that you want to swap axis 1 and 2, meaning that the second and the third axis. So you want to swap the second and the third axis. That is why you write it like this. So then what happens is that you get 4 by 2 by 3 matrix, because you started with the 4 by 3 by 2, right? You started 4 by 3 by 2, and you're swapping the second and third. So that should be 4 by 2 by 3, 4 by 2 by 3, like this. So that's what transpose function does for you when you're dealing with high-dimensional tensors. What about this one? So you're swapping first and second axes, and you're leaving the third axis intact. So that would give you 3 by 4 by 2. 3 by 4 by 2. Right? So please keep this in mind. I'm not sure if the PyTorch tensor tensor library uses exactly the same transpose function as Numpy, but the spirit the spirit, at least, is the same. When it goes to higher order tensors, higher order n-dimensional arrays, transpose is actually just swapping axes. Well, actually, which is the same thing as here, right? You're just swapping these two axes. So you started with 3 by 2, but you arrived at 2 by 3. So that is what's happening here, right? So please keep this in mind. We're now moving on to, I think we're moving on to the final step. Okay, so we're right on time. So broadcasting. So broadcasting is a very, very important concept. You should not mess this up, because this is kind of confusing from time to time. You start with a vector. And you have a scalar value 2, and you're adding them you're summing them together, which should not happen actually, because it should give you a syntax error, because you're trying to add one element, which is a vector, which is 1-dimensional array, and another element, which is a scalar, meaning that it's a 0-dimensional array, right? So the dimensionality doesn't match, but it still works somehow, right? It still works. You can see the end result, 0, 1, 2, and you've added 2 to all the elements. So 0 plus 2 gives you 2, 1 plus 2 gives you 3, 2 plus 2 gives you 4. So that's what happens. So why is it okay? Why does it work? It's because broadcasting kicked in. Okay, so this is what broadcasting is. If you're trying to do some operation, math operations with 2 elements, where one element is higher order dimension, like one element is higher in dimensionality than the other element, then it actually automatically broadcasts if the condition is met. So we'll talk about the condition in the next cell, right? So you can see that all working pretty good, right? And actually, if you divide, oh, actually, yeah, B is 2 points. So this is a float value. So I told you that if you do a matrix, if you do a mathematical manipulation with one element, which is integer, another element, which is a float value, then it'll all be converted to float value. So you can see the end result is all float value. And every single time, B is converted internally to a vector of 2s, like this. Well, actually 2 point. Internal, we don't need this. Yeah, internally is converted to a vector element, vector object, so that the dimensionality matches with A and B, so that these operations can be done, right? So that's broadcasting. So it doesn't work. So there, as I said, certain conditions need to be met in order for that to happen. So we're going to go look at matrix and vector broadcasting first. So A is a 3 by 2 matrix. B is 1-dimensional vector. 1-dimensional array, so which is a vector, right? So this is two-dimensional array, which is matrix. It's a one-dimensional array, which is vector. So this is a matrix and a vector, and you're doing the same thing. You're trying to add them together. What would happen internally, right? So if you wanted to somehow add these two together, then at least B needs to be expanded to a matrix form. It needs to go one-dimensional higher, right? So that's what's happening here. It's the B is being repeated to look like this. Like B would be, oops, 1, 2, 1, 2, 1, 2. Well, yeah, you can. I guess you can. Like this. So now B, so internally, this is what is happening. So B, the vector is converted to or expanded to a matrix like this, so that the dimensionality matches between A, and B, A and B, and then if you sum them together, then you would get this, right? So that's broadcasting. So the question is, what would happen? What would happen if B were this instead? What if B, so we can actually try it out. We can try it out. So B is, we're going to, so B is this. What would happen? It doesn't work. So why it doesn't work? Because the broadcasting condition was not met. So in order for the broadcasting to work, at least the one dimension needs to match with, so as I said, broadcasting happens when one element is larger in dimension compared to the other element, and the smaller element in dimension, I'm going to call it the smaller element. So the smaller element's dimension needs to match with the larger dimension, so that when it's expanded to the upper dimension, the size matches. But here, B is already a two-dimensional matrix, right? It's a matrix. A is a matrix, B is a matrix, and their shapes don't match, so it wouldn't work, right? The former causes error, whereas the latter gives us the input. So latter, I guess you're talking about this one, right? So let's look at this, why this would work, right? 1, 2. So this works. Interestingly, this works. Why does it work? Because the second dimension matches, and it's the first dimension that doesn't match. But the first dimension can be expanded to, like it can be copy-pasted. Like this element can be copy-pasted within 2 more times, so that it becomes 1, 0, 1, 0, 1, and 0, 1. So that it becomes a 3x2 matrix. So that is why it works. But if it's 2x1, there's no way it can work. Question. A가 B에 비해 432처럼 2차원 더 높은 경우에도 내부적으로 동일하게 채워지나요? Good question. You can try it out. You can always try that out. If A was 24, 4x3x2, and B is just simply 2, would it work? And the answer is yes. So 1, 2 will be repeated how many times? It will be repeated 12 times. 12 times to match the A's dimensionality. So it becomes 4x3x2. Then it'll, then it'll work like magic. So it's not always, it doesn't have to be that there's only one dimensionality difference. It can be 2-dimensionally difference, 3-dimensionally different, as we've seen here. This is a vector, and this is a 3-dimensional array. This is 1-dimensional array. This is 1-dimensional array. This is 3-dimensional array. So that is why it works. Actually, it doesn't even, B can be just a scalar value, and it still works. B is like 5. Still works. Then there's like 3-dimensional difference between the two. So this is 0 dimension. This is 3 dimension. So 5 will have to repeat it 24 times, right? Does A should have the same element with B at least in 1 dimension, right? Actually, B has to have at least one same dimension as the A. Or no dimension at all, So yeah, you'll have to try it out like a couple times by yourself to get a feeling of when it works and when it doesn't work. Once you get a hang of it, it's pretty easy. Right, the next one is tensor and matrix. Again, it's the same principle, because this is 2x3 and this is 3x2. At least these two match, right? These two match. So that is why B needs to be repeated one more time so that this becomes 2 by 3 by 2. Then it'll work, right? What happens if it was three-dimensional matrix? So is it sufficient that only one dimension matches? In this case, only this dimension matches, right? Would it work? Like this is 3, this is 3, would it work? The answer is no. It's the last dimension that needs to match. Or last two in this case, or last, or no dimension at all in this case, like in the scalar value type, or no dimension at all. You see what I mean here, right? So if it was 2, there would have been no problem because the last dimension matches. Right? Okay. Hopefully this makes sense. Right, there's one more quiz. You can do it on your own time. And the final quiz, I think we got 10 more minutes until 12 o'clock. So this is a rather involved matrix manipulation function. And see the spec, read the spec. So this is given to you. Define a function that given an m of shape m comma n and a w of shape 4n comma n, and that executes the following. And we're going to assume that m is an even number. It could be 4, 6, 8, whatever, right? And so take the first half rows of m, second half rows of m, odd number rows of m, even numbered rows of m, append them horizontally in the list order meaning this order. And then you obtain a matrix X of shape something. So, well, what would this question mark would be? What would this be? Like, think about it so that you can solve this problem easier. What would this question mark would be? And they'll linearly transform X, which is this guy X, linearly transform, meaning multiplication. They'll multiply X with W. Linearly transform X with W so that you obtain a matrix Y of shape something something. So you can fill the blanks here. And then put Y through the sigmoid function, which is this function. And if you put a matrix, if you put an n-dimensional array into this scalar function, then this function will be applied to each element-wise. Then obtain the sum of the mean of each column. So you first take the mean of each column, and then you sum them. And then you return that number, return that value. So can you do this? So this is just a generic function, and m can be anything, w can be anything, right? M is just some n by n matrix, and w is just 4n by n matrix. So assume that when you're writing this function out, and then return this value, the final value, and test that value with I'm going to give you a test case. And see if you can get the right answer within 10 minutes. So 10 minutes, so actually 9 minutes now, 12, until 12 o'clock. So I'm going to give you until 12 o'clock to fill that function. And then and the test case would be, I'm going to write the test case in the chat box here. Test this one out and see what output you get. And actually, this is we'll call this a bonus quiz. So if you get this right, you'll get a bonus. And give me your answer in a direct message. Don't post it out on the comment channel. Just give me a personal message. Yeah, actually, yeah, somebody gave me a code, but you can actually just give me the answer to that answer using the test case, the M and W that I just wrote down on the chat box. Yeah, linearly transform x with W means multiply x with W, not Y. W. Yeah. It's x dot x. Yeah, it's a matrix multiplication dot product or the et operation. Okay, don't give me so Thawirath. Don't write that in the comment channel. Give me a personal message. Yeah, I'm getting a couple of I'm getting a couple of good answers. Yeah, some people are really fast, so that's good. No, that is not the direct message only to me. You're you're broadcasting your message to everyone. Hope everybody's actually at least trying out the code. Besides, anyone who's not interested in the quiz, you can ask questions, any question regarding the class material today. Don't give me the code. Don't give me the code. I gave you a M and W, the test cases, so you can run that test case and give me the result. 저한테 코드를 주지 마시고 제가 M하고 W를 올려놨으니까 그걸 돌려서 그 결과물을 저한테 주세요. As I said, linearly transformed X with W is AX multiplied to W, matrix multiplication using dot or at. So any questions so far? Some people are giving me a truncated answer, but give me all the digits, subdecimal digits. For example, if you just give me like 5, that is not a right answer. Like it should be like 5.00 something something something, right? M랑 W 저 위에 있을 텐데. 뭐 저에겐 저 위겠죠. 저에겐. 저는 계속 메시지를 받고 있으니까. 제가 올려놓은 게 있을 텐데. I've written the test case down in the chat. You can see the message from me, right? Okay, so there are some questions. So even numbered means 0, 2, 4, 6, 8, yada, yada, yada. Odd number is 1, 3, 5, 7, 9, yada, 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 okay? You know, when you're sending me your answers, please don't ask me if you got it right. This is a quiz, so I can't give you the answer. So while you guys are writing the codes, keep in mind that you should be very familiar with at least like hopefully all contents of today, how to manipulate, how to define the matrix, how to multiply them, how to like mathematically manipulate them, how to slice and dice them, how to transpose them. You should be very familiar and you should have like very clear concept of this whole entire thing in your head. You need to be able to imagine things that are happening here. When seeing the code, you should be able to imagine it in your head, what's happening. So that because all the following practice sessions will never go into this kind of detail anymore, not even once, okay? Like this kind of basic stuff is today only. The next session will be scikit-learn. So we're going to talk about machine learning, and we're not going to go over the matrix manipulation details. So after the scikit-learn, then we'll go into PyTorch, and it'll be like a it's like a fast ride, okay? There's no time for me or actually the TAs to go through all the details step by step. So please, at least go over this at least once or twice again. Especially if you're a newbie, if you've never used Numpy or Jupyter Notebook, please play around with this for at least a couple more times. Otherwise, like starting from next session, it'll be you're gonna get lost track of what the TA is going to say, and then you're gonna have a bad time. All right, it's 12 o'clock, so I'm going to give you 30 more seconds, and then I'm going to end this class. Does a full function have a practical use? No, it's just to test if you've captured the essence of today's material. Okay. All right, I think we have 5 more seconds. All right, it's 12:01. So starting from 12:01 is like all the don't send me the answers because I'm not going to count the 12:01s, the answers that came in 12:01s. So you'll see your own chat and see that you're already this past the time. Okay, so I'm going to read all the answers, all the personal chats to me up until 12:00 and see if it's correct. And if it's correct, I'm going to record your name and give you a bonus point, okay? And starting from next week, next practice will be TA session. Actually, 퀴즈답 추후에 올려주겠습니다. 네. So the practice session from next week will be conducted by TA only. Unfortunately, unfortunately there needs to be some changes to the structure of the course. So usually I did the practice session, the 2 practice sessions up until the next one, but there has to be some structural changes. So TAs will take care of that. So hopefully you've already covered today's material very well so that you can follow the TA's session starting next week. All right, thank you guys very much. And if you have any questions, please post them on Classroom, and I'll see you guys next Tuesday. Bye-bye. 네, 감사합니다. Thank you. Thank you. Bye-bye. 네, 감사합니다. 네, 감사합니다.